Namaste and welcome back to Murali's World of Physics. In my previous video, I had explained some details regarding the game of Carroms and the carom board on which this game is usually played. Now in the second part of this video, I would like to discuss some of the main physics principles involved in this game. In a nutshell, the main concepts that we discuss are the following: forces, velocity and acceleration, kinetic energy, linear momentum, and collisions between objects. The main principles and laws that we discuss are Newton's law of universal gravitation, Newton's laws of motion, and conservation laws. First, we take the case of forces. After all, what is a force? A force is either a push or a pull. In physics, we recognize a force as any interaction, either direct or indirect, that when unopposed will change the state of rest or of uniform motion of an object. A force, in fact, can cause an object to speed up, so this is acceleration, to slow down, that is deceleration, or change direction. So for example, a rocket being fired from the Earth station, it is accelerating up and speeding up. This is a parachuter falling under gravity towards the Earth, but because of the parachute, he is being decelerated. Now here a cannon is being fired at an elevated angle, and because of the gravity, the change, there is a direction change. So these are the three basic effects of a force. In the game of Carroms, several forces come into play. One is gravity. Although it is not as prominent as in some other games, gravity still plays a role in influencing the trajectory of the carom and the queen. What is gravity? It is the invisible force that governs the motion of celestial bodies. In fact, it pervades the whole of the universe. From the apple that fell on Isaac Newton's head to the implications of Einstein's theory of general relativity, our understanding of gravity has evolved quite significantly. One of the most important moments in the history of physics came with the publication of Isaac Newton's Philosophiae Naturalis Principia Mathematica in 1687. In his monumental work, Newton formulated his laws of motion and introduced the law of universal gravitation. According to him, every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So these are the two masses, m1 and m2. R is the distance between the centers of these masses, and these two attract each other. So the forces are equal and opposite. And the formula for this gravitational force is given by G times m1 m2 by r square, where G is known as the gravitational constant. The magnitude of this constant is G is equal to 6.674 into 10 raised to minus 11 meter cubed per kilogram per second squared. In Carroms, gravity comes into play in the following ways. It acts on all the coins and the striker at all times. These remain on the board surface because of the counterbalancing forces due to the reaction of the surface on these pieces. So we have the force due to gravity acting down, and the board counteracts via a reaction which acts on the board in the opposite direction. So as a balancing effect of these two forces in opposite directions, the coin remains stationary on the board. However, when they come over the corner holes, there is no counterbalancing forces in play. Only the gravitational force acts on the coin, and therefore it will fall down into the netted pocket, which is crucial to winning points in the game. The fact that the board surface is plane and horizontal is also a manifestation of the effects of gravity. For example, if the surface is not plane or horizontal, the coins will have a tendency to slide down to one side of the board during the gameplay. And this is bound to change the direction of movement of the coins, obviously. Another important force is the finger force, and this force is applied by the player's finger when flicking the striker. It is this force which determines the speed and direction of the striker. In turn, it also decides the force with which and the direction in which the striker will hit the coins. The players can adjust the angle and force of their flicks to navigate around obstacles or pocket specific coins strategically. The finger force technique offers versatility in the gameplay, allowing players to execute a wide range of shots, including gentle taps for delicate maneuvers or powerful strikes for aggressive play. The origin of these forces lies in the contraction and expansion of the muscles of the finger. When the fingers flick the striker, muscles in the hand and forearm contract, thereby generating a force. And this muscular force is transmitted through the fingers to the striker, imparting momentum to it. The origin of these forces lies in the contraction and expansion of the muscles of the finger. Contact between the fingers and the striker is subject to friction. In fact, this friction enhances the transfer of force from the fingers to the striker. Friction allows the fingers to grip the striker firmly and transmit the applied force more efficiently. Next, we have collisional forces. When the striker hits the Carrom or queen, collision forces come into play, causing the pieces to move in different directions with varying speeds. Now, I just mentioned friction just some time back. What is friction? Friction is the force that one surface exerts on another when the two rub against each other. And the primary characteristic of friction is that it opposes motion always. That means friction acts in a direction opposite to the object's direction of motion. For example, the friction between a coin and the board essentially depends on the reactional force that the board exerts on the coin. This reaction is equal and opposite to the weight of the coin. So the reaction is equal to mg, which is the weight of the coin. So this is as per Newton's third law. The friction between the carom board surface and the striker determines how fast and how far it travels and how it is effective when it hits the other pieces. So this is the coin on the board surface. So suppose the coin is moving in one direction, then the frictional force acts in the opposite direction. Now, the frictional force is characterized by a constant known as the coefficient of friction, which is characteristic of the two surfaces, the two touching surfaces. As I mentioned, the board applies a force in the opposite direction to that of gravity, and this is known as the reaction of the board on the coin. Since these two are equal and opposite, the coin will remain on the surface of the board unless it is acted on by an applied force, which obviously will be due to the striker. So when it is in movement, the friction direction of motion of the, and it is given as mu times mg or mu times the reaction. So mu is nothing but the ratio of the frictional forces to the reaction. Without friction, an object in motion would continue to move at a constant speed for hour as per Newton's first law. The strength of the force of friction depends upon two factors, typically the types of the surfaces involved and how hard the surfaces push each other. In fact, I had done an earlier video giving some basic details about the frictional forces. So you can watch it in my YouTube channel, Murali's World of Physics, and the link is given here. Another force which comes into play, although not to that extent as the other forces, is the air resistance. Though minimal, this affects the movement of the striker and the carom pieces, slowing them little bit, slightly, as they move across the board. Now, several basic physics laws are involved in the game of caroms. Of course, the Newton's laws of motion. The first of this is the law of inertia. This law states that an object will remain at rest or in uniform motion in a straight line if it is already moving, unless it is acted upon by an external force. So in fact, this defines force. Now, considering the carom pieces on the carom board, so when nothing is going on, that means when the game is not being played, the pieces are stationary on the board is stationary, the coins are also stationary. That means there are no net forces on the board, striker and the coins. That is why they keep on being at rest. Now, Newton's second law of motion, otherwise known as the law of acceleration, it actually gives the effect of a force in terms of the acceleration produced in the object on which the force acts. So this law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So Newton's second law is stated in the form of an equation, F is equal to ma, where m is the mass of the body, F is the force acting on the body, and a is the resulting acceleration. In fact, this is a vector equation, meaning that the direction of a will be the same as that of the direction of the force. So the force is directly proportional to the mass of the body, or in other words, the acceleration, which is the effect of the force, is directly proportional to the force acting on the body and inversely proportional to the mass of the body. When the striker hits the coin, a force is applied, and this determines the acceleration of the coin, and of course the mass of the striker affects how easily it accelerates. So there is a acceleration produced because of the action of the force on the coin, and obviously the force is caused by the striker striking the coin. Coming to the third law of motion, which is basically the law of action-reaction. So this law states that for every action there is an equal and opposite reaction. So this we have already seen, the coin staying stationary on the board is activated, the coin is acted upon by the gravitational force mg, where m is the mass of the coin, and in turn the surface of the board applies an equal magnitude force in the opposite direction, and this is known as the reaction. So Newton's third law states that action and reaction are equal and opposite in direction. When the striker hits a carom piece, it exerts a force on that piece, and the piece exerts an equal force back on the striker. Consequently, the coin accelerates in the direction of the force and the striker decelerates. Now, associated with force there are two quantities which are called work and energy. We know that a force acting on an object produces an acceleration in its direction, thereby increasing the velocity of the object. Now, in doing so, the object will move through a certain distance in the direction of the force. Let's say d is the distance moved by the object. So we say that work is said to be done on the object by the force. And how much work is done is measured by the product of the force and the distance d. That means W, the work done, is equal to F into d. Well, we know that F is a vector quantity, d is typically the displacement, it is also a vector. So actually we have to have dot product of these two vectors. So therefore work done is equal to the product of the force acting along the direction of movement. So we have to consider the component of the force along the direction of the movement and take the product with the actual distance travelled along that direction. Now it is this work done which appears as kinetic energy of the body. So kinetic energy is a measure of the work done by the applied force on the object. Now another important quantity is the momentum. What is momentum? It is a measure of the motion of the object and is measured via the product of mass and velocity. So the momentum P is equal to m into v. Now P also is a vector quantity. It is in this direction of the velocity. So the magnitude is given by the product of the mass and the speed, and the direction is the same as that of the velocity. Now as per Newton's second law, F is equal to m into a, but what is a in terms of the velocity? Acceleration is nothing but the rate of change of velocity. So a is equal to dv by dt. So force is equal to m into dv by dt. Now mass typically is a constant property of the object. So therefore one can treat m as a constant here, and that can be taken inside along with velocity. So we can take the product m into v and take the derivative with respect to time. So F is equal to d by dt of the quantity mv, but mv is nothing but the momentum. So therefore force is equal to dp by dt. Hence a measure of the force is given also by the rate of change of momentum of the object. Now if we take infinitesimal time and the corresponding change in momentum, F is equal to m delta v by delta t. So that is equal to delta p by delta t, since mass is a constant. And if you rearrange, just take delta t to the other side, we have F delta t is equal to delta p. So therefore if there is a force acting for a very short period of time, delta t, there is a change in momentum of the particle which is given by the product of F and delta t. So this particular product is called the impulse of the force. So impulse is nothing but a force acting on an object for a short period of time, and the product of the force and the time period gives as a measure of the change in momentum of the particle. Thus the result of an impulse is a change in the moment of the object. Impulse occurs during collisions between the striker and the carom pieces, as well as among the carom pieces themselves. And of course the collisions of the striker and carom pieces with the edges of the board also. Understanding impulse helps players predict how pieces will move after a collision. As per Newton's third law, the force FAB exerted on B by A is equal and opposite to the force of BA exerted by A by B on A. Thus FAB is equal to minus of FBA. But each of these forces is given by the rate of change of the momentum of the object on which the force is exerted. Therefore, the rate of change of momentum of B should be equal to minus rate of change of momentum of the object A. Or in other words, d by dt of PA plus PB is equal to 0, and therefore the quantity PA plus PB, namely the sum of the momenta of the two particles, is conserved. So therefore, this is the famous law of conservation of momentum. It states that the total momentum of a closed system remains constant if no external forces act on it. That's a precondition, that there should not be any external force acting on the system, and then the total momentum will be constant for a closed system. So we have two masses colliding with each other, m1 and m2. Their momenta are m1 u1 and m2 u2, and after collision their velocities are different now. So the new momenta are m1 v1 and m2 v2. So therefore, the total momentum before collision m1 u1 plus m2 u2, that should be equal to m1 v1 plus m2 v2. So that is the law of conservation of momentum. In Carroms, when the striker hits a piece, the total momentum of the system, that means the striker and the piece before collision, should be equal to the combined momentum after the collision. Now coming to the second important conservation law, namely conservation of kinetic energy. We know kinetic energy is the energy, that means the ability to perform work, possessed by a body by virtue of its motion. So how do we measure the kinetic energy? The kinetic energy is measured as the quantity half m u squared. M is the mass of the particle and u is the velocity. In a limited set of collisions, the total kinetic energy of the colliding objects remains a constant. So half m1 u1 square plus half m2 u2 square. This is the initial kinetic energy. Maybe this is that of the striker and this is that of the coin, or maybe both these are coins. So that should be equal to the total kinetic energy of the particles after the collision. So they may be moving in different directions with the different velocities. So we take the total momentum after the collision, that is numerically equal to the total, so the velocities may be different in different directions. We take the total kinetic energy after the collision, that should be equal to the total kinetic energy before the collision process. So during the collision, momentum and kinetic energy are transferred between the striker and the struck coin. So this transfer of kinetic energy and momentum to the coin causes the coin to move. Of course, the direction may be different. In this context, we distinguish two types of collisions depending on the kinetic energies. One is the elastic collision, where the total kinetic energy is conserved. Here, some of the kinetic energy of the striker is transferred to the coin, causing it to move, while the remainder is retained in the striker. In an inelastic collision, the total kinetic energy is not conserved. So there is a major difference between elastic and inelastic collisions, whether total kinetic energy is conserved or not conserved. What happens to the kinetic energy that is missing in the process? Well, this missing part of the kinetic energy of the striker is transferred to the coin, causing it to move. So here, some of the kinetic energy of the striker is transferred to the coin, causing it to move. A part is retained in the striker, and the balance, the remainder, is dissipated in the form of sound and heat due to the frictional forces. The total energy of the system, including the kinetic energy and the energy transformed into heat and sound, will always be conserved. So that is as per the law of conservation of energy. So the total energy, in whatever form it exists, of a system will be conserved. But of course, there can be transformation between the different forms of energies. In elastic collisions, the kinetic energy is also conserved separately. So that distinguishes elastic collisions from inelastic collisions. Now, in the case of inelastic collisions, we recognize a characteristic of the bodies, namely the coefficient of restitution. It is denoted by E, and it is a measure of how much kinetic energy is conserved during a collision. Therefore, it is a measure of the elasticity of a collision between two objects. E represents the ratio of the relative velocity of separation to the relative velocity of approach of two colliding objects after a collision. Mathematically, the coefficient of restitution is defined as the ratio of the relative velocity of separation to the relative velocity of approach. In the context of linear collisions, that means collisions along a straight line, as in the case with the Carrom board, the coefficient of restitution typically depends on the components of the velocities along the direction of collision only. In simples, we can write the COR as E is equal to minus V2 minus V1 divided by U2 minus U1. U and V represent respectively the velocities of the objects participating in the collision before and after collision. One is for the first particle and the two is for the second particle. So we have, this is the relative velocity after collision and this is the relative velocity before collision. You take the ratio and take the negative of this. So that defines our coefficient of restitution. The magnitude of the coefficient of restitution ranges between 0 and 1. So let's take E is equal to 1. This indicates a perfectly elastic collision where kinetic energy is conserved and the objects bounce off each other without any loss of energy. So the relative velocities before and after collision are equal in magnitude. On the other extreme we have E is equal to 0 and this denotes a perfectly plastic collision, perfectly inelastic collision where the objects stick together after the collision and the kinetic energy is completely lost. And in between these two extreme cases we have 0 less than E less than 1, which are partly elastic and partly inelastic collisions. Which are basically inelastic collisions. So here some kinetic energy is lost during the collision and the objects may stick together or deform. The coefficient of restitution depends on factors such as the material properties of the Carrom coins and the surface of the Carrom board. It also depends on the shape and surface roughness of the objects. In the game of Carroms, a higher coefficient of restitution implies a more elastic collision where kinetic energy is preserved to a greater extent. The COR depends on factors such as the material properties of the Carrom coins and the surface of the Carrom board. Now combining the two conservation laws, we get U1 minus U2 is equal to U2 minus V1 or E is equal to U2 minus V1 by U1 minus U2, that is equal to 1. So when linear momentum as well as kinetic energy are conserved, we end up in an essentially elastic collision.
If you like this video, kindly click on the like button and share with your friends and relatives and also with your different groups. If you have not already subscribed to my channel, World World of Physics, kindly do it now. And please don't forget to click on the bell icon so that you will receive notifications in future about my upcoming videos.
Goodbye.